Educator Carlos Plain of Durham School states, "Most certainly, I went through my whole time on Earth encouraging a particular speculation of the universe, and by, the speculation is being tried. I welcome that because that is how we push ahead, that is how we gain ground in science." The James Webb Space Telescope is disturbing a great deal of what has been viewed as truth in cosmology for the new years. Another ultra-deep picture shows that we have committed blunders in cosmology. The telescope, which was supposed to show us the essential stars of the universe, is transforming into an adversary of the past point of view and may present to us an entirely new science. Not all investigators are cowering in fear at the new realities. Various specialists welcome the developments, since it has long been clear that something was the matter with our old hypotheses. The aberration in the assessment of the expansion speed of the universe alone should have shaken researchers' consciousness long ago. Yet, all things being equal, they adhered to old hypotheses. The cosmic microwave background, CMB, considered the most settled light in the universe, was made about 380,000 years after the Big Bang, when the universe had cooled enough for electrons and protons to form stable hydrogen particles. Investigators call this headway reionization, which made the universe vulnerable to light. The CMB was first seen in 1964 by American physicists Arno Penzias and Robert Wilson while they were managing another kind of radio-receiving antenna technology. This revelation was for some time seen as potentially the most powerful piece of evidence for the Big Bang theory, earning Penzias and Wilson a Nobel Prize and an undeniable spot in the history of astronomy. The CMB likely offers a review of the energetic universe, with little temperature differences providing critical information about the conditions shortly after the Big Bang. Scientists used the CMB as a strong etching of the fundamental estimations of the material universe to check the expansion speed of the universe, among various other things. The astronomer Edwin Hubble had previously resolved this in the late 1920s, finding that faraway galaxies recede from us in every direction, and that their speed is proportional to their distance. Today, these observations are known as the Hubble law or the Hubble constant. Hubble didn't have the high-level assessing strategies available many years later when the CMB was found, which led to a recalculated expansion rate, generally lower than Hubble's original figure. Later scientists recalculated the rate again using type Ia supernovae as standard candles, providing stable light that could be used as a reliable measuring point. The assessments within the CMB yielded an expansion speed of around 67 kilometers per second per megaparsec, while assessments using supernovae yielded around 74 kilometers per second per megaparsec. What does this discrepancy in determining the expansion speed of the universe truly tell us? Did you realize that this mistake has been known since the 1990s? Since then, researchers have known, or at least suspected, that something might be wrong with the examination of the CMB, the assessment techniques, or the prospect of the universe's expansion. The irregularity between the different assessed potential values of the expansion rate is known in science as the SAA tension or Hubble tension. The implications of this strain are enormous, suggesting that critical portions of how we interpret the universe might be damaged. For quite a while, experts were confounded. Since the James Webb Space Telescope went into operation, it has given analysts amazing data that may now uncover insights into the issue of the expansion speed of the universe, with systems so old and mature that their development should theoretically begin before the Big Bang, overturning old cosmology. Researchers no longer discuss errors or assessment contrasts. They now discuss the biggest crisis in modern astronomy. Not only could the expansion rate be misguided, but the whole idea of the Big Bang itself is being questioned. New observations provide evidence of a universe completely different from what we have long believed. The SAA pressure was the first rebuke to experts who still have faith in old theories, and now they face a dilemma. Do we really know much about the universe? Various scientists stand on the remnants of their once firm beliefs, grappling with space with both horror and curiosity, trying to come to terms with what they find. Considering the crisis in science, we ought to ask ourselves what we truly know about the universe. To answer this, we need to understand how science works. Theoretical scientists use a complex web of mathematical models, careful data, and logical reasoning to draw conclusions from the general to the specific. Their understanding comes from a mix of observation, idiosyncrasies, preliminary outcomes, and speculative assessments. The term theory alone shows that these are constructs and considerations, not absolute pieces of knowledge. The only feasible data we have are the photos telescopes provide, the sound waves and radiation gathered with radio telescopes, and the latest data from neutrino assessing systems or gravitational wave detectors. With the James Webb Space Telescope, we now have an instrument that can isolate the most established light into individual frequencies and analyze it in marvelous ways. Webb can show us the pervasive parts in ancient galaxies more than 13 billion years ago, how much mass they contained, and how many stars were present. Can also reproduce the shape and course of a galaxy's evolution. Webb can also have limitations. For example, it can't always determine with certainty whether we are seeing galaxies or black holes with enormous gathering circles that radiate as brightly as a galaxy. We must face the reality that our science has long recognized an excessive number of possibilities as facts and dismissed alternative explanations. Research has long been confident in its accuracy, but the latest revelations from the James Webb Space Telescope are imperative clues to replace old hypotheses with new insights. As often happens in science, analysts are once again holding their breath as they try to come up with new explanations. The new discoveries shake the foundations of our current scientific understanding, alarming many experts. The present theories of physical science are still commonly founded on Isaac Newton's assessments from the 17th century. His laws of motion and gravity formed the foundation of our understanding of the physical universe for many years. Newton's laws adequately describe the motion of things under normal conditions and function superbly on Earth. However, in space, his considerations needed expansion, which was mostly done by Albert Einstein at the start of the 20th century. Einstein's remarkable theory of relativity, published in 1905, revolutionized how we interpret reality, showing that measurements are relative to each other and dependent upon the observer's motion. His general theory of relativity, published in 1915, expanded this thought with mathematical affirmations of gravitational anomalies, including the bending of spacetime by masses like stars or galaxies. Einstein's principles and ideas were groundbreaking in many areas, but he also knew their limits. He realized that his theory would never fully describe the universe, and he longed to see a unified theory that could explain everything. To this day, no scientist has completed that picture. Where is the missing piece? Wouldn't it be fascinating to know where it lies? Michio Kaku, a notable astrophysicist from the USA, said in an interview that solving this issue could certainly win a Nobel Prize. So, let's explore whether scientists have overlooked potential misinterpretations or whether our telescopes are to blame. Dark matter and dark energy are at the top of the suspect list for the real reasons behind the cosmological crisis. Our current models of the universe incorporate ideas that dark matter and dark energy make up around 95% of the universe. However, neither has been directly observed, and their true presence has never been confirmed. They might not exist at all, requiring new explanations for the universe's development and the behavior of galaxies. Alternatively, they could have properties we don't yet understand. One possibility is that the actual properties of dark matter and dark energy have changed over time, potentially showing some kind of insight. Gravity is another concept that needs to be more rigorously tested. This force, which provokes interest through mass or curvature in spacetime, has not yet been fully explained. The considerations of spacetime curvature mostly originate from Einstein and have been confirmed conventionally. However, we cannot dismiss the possibility that gravity has unforeseen properties or that another effect causes the gravitational attraction between objects over time. Several constants have been established in cosmology and astronomy, shaping our understanding of the universe. The study of the cosmos has always been a journey driven by our enduring desire for knowledge and discovery. From early human advancements observing the stars to current space telescopes probing the depths of the universe, each step in progress and theory has uncovered new mysteries while challenging established beliefs. In the field of cosmology, the James Webb Space Telescope, JWST, stands as a testament to our scientific advancement. It promises to change how we interpret the universe's beginnings and evolution. Launched with exceptional capabilities, JWST represents a leap forward in observational space science, prepared to look deeper into reality than ever before. The CMB, often referred to as the glint of the Big Bang, provides a snapshot of the universe as it existed only 380,000 years after its first emergence. This ancient radiation carries vital information about the universe's early conditions, including temperature fluctuations, which are crucial for understanding the development of galaxies and large-scale structures. The error in the calculated values of the Hubble constant, known as the Hubble tension, has been a subject of extended debate. It suggests that something is off with our fundamental understanding of the universe and its origins. Webb's discoveries challenge traditional hypotheses and demand a reassessment of whether our view of cosmic evolution is incorrectly established. New observations may reveal unseen aspects of the universe's creation, raising questions about dark matter and dark energy, two mysterious components that constitute most of reality. The future of science depends on our ability to reshape our hypotheses in light of new information. JWST's mission exemplifies this pursuit. Its discoveries will serve as a foundation for future cosmological discussions and may spark new perspectives on the universe's mysteries. The future of cosmology may witness significant transformations, leading to broader implications for our understanding of the universe, from the Big Bang to the ongoing processes that define its fate. The answers to the great cosmic puzzle may lie beyond our current comprehension, and Webb's observations could ultimately be pivotal in uncovering new truths that may reshape our understanding of reality itself. The discoveries made by the James Webb Space Telescope, JWST, are continuing to challenge long-held beliefs in cosmology and astrophysics. As one of the most advanced observatories ever launched, JWST is capable of peering into the deepest recesses of space and time, providing us with a view of the universe as it was billions of years ago. Unlike earlier space telescopes, which were limited by their sensitivity and wavelength range, JWST's advanced infrared capabilities allow it to observe distant galaxies, stars, and other cosmic phenomena in unprecedented detail. These observations are rewriting our understanding of key cosmological processes, from the formation of the earliest galaxies to the nature of dark matter and dark energy. One of the most significant implications of JWST's observations is its potential to resolve the long-standing mystery of galaxy formation. For decades, astronomers have debated how the first galaxies formed after the Big Bang. Previous models suggested that these early galaxies were small, faint, and scattered across vast distances. However, the images provided by JWST are showing much more complex structures. Some of the galaxies observed by the telescope are far larger and more mature than previously thought, suggesting that the processes behind galaxy formation might have been more rapid and violent than we had imagined. These revelations force us to reconsider our understanding of cosmic evolution, particularly the timeline of the universe's development. The telescope has also provided crucial data on the early stages of star formation. By observing galaxies that are billions of light years away, JWST is able to capture the light emitted by some of the first stars that lit up the universe. These early stars, known as population 3 stars, are thought to have played a critical role in reionizing the universe. They were composed almost entirely of hydrogen and helium and are believed to have formed very early in the universe's history. While no population 3 stars have yet been directly observed, JWST's sensitivity may soon allow scientists to glimpse their faint signatures, providing a glimpse into the very first moments of stellar evolution. One of the most exciting aspects of JWST's mission is its ability to study exoplanets. The telescope is equipped with instruments capable of analyzing the atmospheres of distant worlds, providing insight into their composition and potential habitability. Some of the most intriguing findings are coming from the study of exoplanet atmospheres, which may contain clues about the presence of water, methane, and other molecules that are essential for life as we know it. These discoveries are expanding the field of astrobiology, as scientists are beginning to search for signs of life beyond Earth more seriously than ever before. As JWST collects more data, it is likely that new exoplanets will be discovered, some of which could be in the habitable zone of their parent stars, where conditions may be conducive to the development of life. Another area where JWST is making strides is in the study of black holes. The telescope has already provided new insights into the nature of supermassive black holes, which are thought to reside at the centers of most galaxies, including our own Milky Way. By observing the interactions between galaxies and their central black holes, JWST is offering a deeper understanding of how these enormous objects grow and influence the galaxies around them. One of the most tantalizing questions in astrophysics is how black holes formed and evolved over cosmic time. Did they arise from the collapse of the first stars, or did they develop through some other mechanism? With JWST's ability to observe distant galaxies and their central black holes, scientists are hopeful that we will be able to answer this question and refine our theories of galaxy and black hole evolution. As much as JWST is helping us answer many of these pressing questions, it is also raising new ones. For example, one of the most significant discoveries so far is the realization that some of the galaxies observed by JWST appear to be far more evolved than previously expected for their age. This has led some scientists to wonder if our models of cosmic evolution are incomplete or flawed. Could the processes of galaxy formation, star formation, and black hole growth have occurred much faster than we thought? Are there unknown factors at play that we haven't yet accounted for? These new questions are prompting astronomers to reconsider not only the timeline of cosmic history, but also the mechanisms that drive the evolution of the universe. The study of dark matter and dark energy is also progressing thanks to JWST's observations. While these two mysterious components of the universe remain largely invisible, their influence is felt in the way galaxies and large-scale structures move and evolve. Dark matter, which makes up about 27% of the universe's mass, exerts a gravitational pull on visible matter, but it doesn't interact with light, making it extremely difficult to detect. Dark energy, which is thought to account for around 68% of the universe's energy content, is responsible for the accelerated expansion of the universe. JWST is helping to uncover clues about both of these enigmatic substances by observing how they affect the formation and distribution of galaxies. By mapping the locations and movements of galaxies with greater precision, astronomers hope to learn more about the true nature of dark matter and dark energy, and how they shape the cosmos. Despite the excitement generated by these discoveries, the work of the James Webb Space Telescope is far from over. As it continues its mission, the telescope will provide even more detailed images of distant galaxies, stars, and exoplanets, offering a wealth of data that will keep astronomers busy for years to come. Every new discovery made by JWST has the potential to reshape our understanding of the universe, forcing us to rethink long-standing theories and ideas. It is clear that we are living in a new era of cosmic exploration, one in which the boundaries of our knowledge are being pushed further than ever before. With each passing day, we come closer to answering some of the biggest questions in science. But as we gain new insights, we also uncover new mysteries that will fuel the curiosity of future generations. The future of cosmology is bright, and the James Webb Space Telescope is playing a central role in this exciting journey.